Okay, we're coming in. Joining us here. Let's see. Green screen, treat me okay. Good morning, everyone. Let's fire up some slides here. Let's fire up the right slides. Good. All right, and we should be ready to go. All our technology is in place. We are here, and good morning, Internet. Live from Santa Barbara, live from Winter Hall, down in the basement of the Computer Science Department. We are in Mayterm. This is CS-030, programming in Java, abstract models for concrete problems. This seminar is part of a 5-week class that we're offering, and today's lecture is scheduled for 2 hours. We have a couple people sick and out this morning, which is too bad. The weather has turned nice again, but it is freezing this morning in the basement. So we are communicating in real time on Slack channel. Got a couple people monitoring that. If you have access to it, we're at #broadcastquestions. And we got a new picture up. The flowers outside are beautiful. One of the cool things about spring in Santa Barbara is there's just flowers everywhere, and they're kind of dramatic. So this is nasturtiums just growing wild off campus. It's amazing that that grows wild. And they're edible too. So if you ever get hungry, just go out there and graze a bit. You and the cows. Okay, so we're arriving from a lot of different places. I was just telling the team here that this morning we picked up an HTC Vive Pro virtual reality kit from FedEx this morning downtown. So I've been running all over the place and can use a second to just arrive, make sure that our notifications are off. Just take a deep breath. Okay. Remember, just higher level, what we're doing with all this stuff. And we've been talking about, got a lot of different things, but I want to circle back to some of the ideas that we've been talking about with regulation. And we had been talking about the way in which regulation in society happens in a lot of different ways. A few of them as enumerated by Lawrence Lessig in his book Code and Other Laws of Cyberspace were these ways in which law, a institution that we're kind of used to in terms of regulation, regulates us. We see this all the time in the U.S. national politics. What laws are we considering? What laws are good? What laws are bad? What laws are failing? What laws need to change? Mostly around regulation of behavior, whatever the hot button topic is today. Abortion, gun control, gender, defense, spending, ethics, all kinds of stuff that we're talking about publicly about regulation. But a lot of regulation also happens in other institutions other than law. For example, social norms. We have expectations of each other that are not regulated legally, but we expect through various kinds of interpersonal negotiations us to behave in different ways. We don't expect other people to be using our stuff without asking for permission. All kinds of things like that. We're also regulated by market forces, so the economics of certain things prevent us from doing things because they cost a lot or they're expensive, or they encourage things because they're cheap. So we might choose to park in one way or another based on the cost of parking, or we might choose to shop in one place or another because of the cost of food at the farmer's market versus Vons versus Trader Joe's. But importantly for this class, code also becomes a location where regulation gets enacted, because code ends up dictating the ways in which we can move through our world. It is beginning to move out, it's not even beginning to, it's really been moving out for quite a while now from the spaces of our computers into the world in which we inhabit. And we talked a little bit about how much code is involved in regulating our movement at the airport, and I want to circle back around to that idea a little bit. Two authors, Kitchen and Dodge, in a book called Code/Space, make this argument for the way, and kind of expand on this argument for the way in which code is structuring our physical space now. Increasingly software is becoming part of our movement through space. And I think the airport is a really interesting place to think about this, because if you kind of look at the physical arrangement of the airport gates and like moving into the secure area, there's not really a whole lot of physical barrier from preventing you from just walking through. Yeah, you might have to push through a security guard, but if you made a break for it, you could physically get through there pretty quick. And people would chase you down and there'd be security alerts and whatever. But it's not really a physical barrier that's what's preventing you from getting through. As you are moving through, as your body is moving through this security arrangement, maybe a pat down, maybe some sort of digital scanning, it's interesting to think about the fact that there's also a virtual version of you. There's essentially an avatar. We're used to maybe Avatar from games or maybe from the movie Avatar. But there's an avatar of you that is also moving through the gates as well. There's a digital representation of you that has to move through the system as well. So as your body is moving through the gates, you also have this object, this identity, that has to move through some databases as well. So you have to present the right credentials physically in order to move your data from an unsecure position to a secure position. You can't get into your plane unless your digital identity has gotten through this gate. In order to get your digital identity through the great gate, you have to present physical credentials. And when you present those physical credentials, like a boarding pass, it might not actually even be physical because it might be on your phone or something. Your digital avatar is evaluated. It's evaluated against watch lists. It's evaluated against maybe random security screening. It's evaluated against anything new that's happened in some sort of monitoring. And so there's kind of two parallel things that are happening. You are moving through the gate, and you have to do the right things to get your digital avatar through the gate. And what you do physically affects whether or not your digital self can get through. And what your digital self does affects whether or not your physical body can get through. And thinking about these two different things, I think starts to make us think about the world a little differently, because we often have these digital avatars that are following us along that also need to get through the system. So for you guys in school, you can think about trying to graduate from school. On the one hand, you show up to class, or if you're remote, you show up remotely, and your physical body is there. Great, so you learned something. But it's not enough to just show up in class in order to graduate. You also have this digital identity that exists with the registrar. And that digital identity has to move from being a first-year student to a second-year student to a third-year student, and eventually, to get a diploma, your digital avatar has to move through the system as well. What has to happen for your digital self to move through the system? Well, you need to show up in classes physically. And when you show up for a semester, your digital avatar moves forward a little bit because you get grades, and if the grades are good enough, then you get to progress to being a second year. And so there's this other representation of you that's moving as well. And if you continue to put your physical body in the right space, and your digital avatar continues to align itself with the right classes and sign up for the right gatekeepers, then eventually you pass through college and you get this degree. But it's these two things working in parallel. And that part of you that's the digital avatar is completely controlled by code. And because that bit of code impacts what you do physically, you see the rules of code start to impact what you do in physical world. Which rooms you go to, which classes you pick, which seats you sit in some cases. Very kind of interesting to think about this. Then when we take it into this class and what we're doing, well, what is that digital avatar like? In many cases, it's just an object. Like we've been creating classes. We're just creating these objects that are going to have instance variables, which are representations of your grade or your person or your social security number. And the rules, the behavior that we build into those objects in terms of methods end up, enforcing various kinds of constraints on you in the physical world. Usually it's not just one object, it's usually lots of objects. And those objects get stored in databases and come back and whatnot. But kind of an interesting dynamic of what's happening as we think about the role in which code starts to take as it pervades all the different systems and institutions that we're a part of. So that's the big picture thought. What else can we talk about? What about the details? So for the class today, paper exams are still delayed. Why? This is my bad. So we've got one student out there who still needs to take the remote exam. They were all ready to go, and I didn't synchronize it with the Proctor Free service, so it didn't show up when they went to take it. So sorry, random unnamed student out there. It should be set up now correctly, and I've communicated with you through Canvas to get that ironed out. We have a programming assignment on generics due on Friday. Today is Thursday, so that'd be tomorrow. And we have a quiz on generics due tomorrow as well. We have a quiz on recursion due on Monday, and we're going to be talking about recursion today and tomorrow. That's chapter 13. So today and tomorrow is chapter 13. Monday we'll talk about the drone assignment and work through that a little bit. And then on 3 lectures next week, we'll talk about tree data structures, something that I don't think we've looked at very much either in CS-10 or CS-30. Then we have a final exam. Boom. Any thoughts? Any thoughts out there online? Yeah. Fast. It's good. All right. It's gone by fast. That's the thought. Okay, so last time. Last time we were wrapping up generics, and we did a few things in class. We had already transformed our linked list implementation into an implementation that accepted generics. We acted as systems programmers to do that, and when we changed our implementation to use generics, we had to use a class-based generic where we put brackets and some kind of a letter typically at the top of our class definition. And what that enabled our class to do is to use that letter as a standby for any kind of object reference that we wanted to, so that we could think about manipulating the references as a list or as a set or as a hash map, whatever it was we wanted to do, independently of what we were storing. Because when you have a list, it doesn't matter whether it's a list of strings or a list of integers or a list of doubles or a list of identity objects or a list of whatever kind of class you come up with. What's important is that it's ordered and that you can count them and that you can replace them and move them and iterate over them. So we did that in linked lists, and then we did that with array list implementation. We had to negotiate a few difficulties because we knew that primitive types like arrays and generics don't work well together. So we had to find our way through that. But once we had built our linked list and our array list implementation using generics, making our queue and our stack implementations work as well was pretty straightforward, I felt. Maybe the trickiest part about our implementations of queue and stack were that when we were writing our queue and our stack implementation, we were acting kind of simultaneously both as an application programmer and as a systems programmer. So to the degree that we were creating a class called queue that other people were going to use, we were a systems programmer. But because we were using array list internally in order to create that queue, we were acting as an application programmer using the array list class internally. So real common thing that happens is that as you implement some new class, you're also using some other class in order to create that new functionality. We did a pattern which is called wrapping a class in this case, meaning that we had an instance of a different class embedded within our class, hidden away and encapsulated from users of the queue class. And so the users of the queue class didn't know whether we were implementing it with an array list or a linked list. And they didn't need to know because the behavior of the queue is independent of the implementation. That's a running theme throughout object-oriented programming. Implementation and encapsulation are different than the abstract ideas that you're trying to implement. We also looked at the difference between generic methods and generic classes. So on the right here is just a reminder of a generic method. And so this is a method that has a generic type, in this case T. And you can see that in this, what we did here in order to represent the generic type was we put this T right here. And this said, because we put this here before the definition of the function, this means that we could use this variable any place we wanted to in the rest of our method declaration, the rest of our method implementation, in place of a class. So we might want to substitute in, when someone uses our method, they will have to substitute in this T, or the compiler will do it for us, so that we can get consistency between what is being stored in our list and what it is we want to replace all those elements with as we go through this loop. And then the last thing we did is we looked at some specific examples of working through generic methods, and we had that algorithm, that max algorithm item we looked at the end, where we tried to make that work correctly in a generic manner. All right, so now we're going to think about something different. Generic classes, we've done a lot of work up to this point thinking about implementing classes and how are the different ways we can leverage features of the Java language to represent what we want to represent. Recursion is a different way, it's a different sort of subject matter. Recursion is about solving problems. And so recursion, we have these classes and objects that we can use as part of solving problems, but recursion is a family of algorithmic approaches to tackling different kinds of problems that you might want to solve. And thinking recursively is this specific kind of different way of thinking that takes a little while to get your head around, and it's very mathematical in its nature. And it has some really remarkable power if you are able to apply it to the right problems. So we want to practice thinking recursively. We want to look at using recursive helper methods. We want to think a little bit about the difference between recursion and iteration. To the degree that we have time, we're going to look at the recursion effects of efficiency of algorithms, and then look at ways in which we can use mutual recursion. So to refresh ourselves, because I know we've all seen recursion before in the context of Python, the concept is the same, it's just implemented in a different syntax. The basic idea of a recursive method is a method that calls itself. This is a simple definition. So this little diagram on the right shows that you have some method out there, and that arrow represents calling another method. And then down this loopy arrow represents this method calling itself. And it is this call right here that makes a method recursive. So asking whether or not a particular method is recursive requires you to identify a place within this method where it's calling itself. That makes it recursive. Now that's a simple definition. It's pretty straightforward, I think. Recursion can actually be a little bit more complex, and I want to complexify that definition just a bit by showing that recursion is actually anytime there's a circular chain of method calls. So if a particular method calls itself, well, that's a circular chain. It's just calling itself. But you can actually have a more complex circle where some method calls method A calls method B calls method C calls method A again, and then that circle is now there's a circular chain of method calls, but it's not method A calling itself. It doesn't even necessarily, it's not even immediately apparent if you just look at method A that this is recursive. You would have to look at the entire structure of method calls to see that this could be a loop that just calls itself forever if it isn't properly designed. So more generally, recursion is any sequence of method calls that forms a circle or some circular pattern. And this is an abstract circular pattern, right? You need to think about it because when you see it in code, it's just going to be method calls like println or calling your own method, calling fill, calling a constructor. But in practice, you'll have to sort of abstractly understand that there's this sequence of looping going on. To do recursion well then, because you have this looping pattern, in order to implement it well, you need to make sure that this looping can stop at some point. And so thinking about recursion entails thinking mathematically in an inductive style of thinking, meaning, hey, I have this problem I need to solve. If I could solve a smaller problem, I would know how to solve this bigger problem that I'm trying to tackle because I can break it down into smaller problems and then somehow combine those smaller problems together. So recursive thinking says, well, let's assume I can solve the smaller problem, put that aside for a second, and if I make these method calls that are going to solve the smaller problem, what I get back from those method calls I can combine in order to solve my larger problem and then return. And as long as those problems are actually getting smaller, you have a good chance of being able to find a solution. So for recursion to be well-formed, meaning a recursive loop to actually be helpful rather than just going on forever, there's got to be a stopping condition. At some point, you've got to stop that loop and go back the other direction as you return from method calls. Otherwise, you end up in this infinite circle, just like you can end up in an infinite while loop, or in principle, an infinite for loop, although that's harder. And if you do that, if you end up in an infinite circle, you're going to end up having what's called a stack overflow. Stack Overflow, you know more generally from the website Stack Overflow, where you can search and find solutions to different coding problems, hopefully not our homework, but nonetheless, certain kinds of solutions to specific problems. That's the name of the website, but the name of the website gets its name from this problem of calling too many functions. And each time you call a function, you add a frame to something called a stack. The stack is just like the data structure stack, but what we're keeping on this particular stack are function calls. And so as you add more and more function calls, and as you return from function calls, your stack gets bigger and smaller. If you make too many function calls, you run out of space for your stack, and you get a Stack Overflow error, and your program crashes. So for recursion to be well-formed, you've got to have a stopping condition to prevent the stack overflow. And in order for you to get to that stopping condition, each successive call through that circular pattern has got to make the problem a little smaller. Or maybe more specifically, each call's got to be getting closer and closer to that stopping condition. Because eventually, if you're not getting closer and closer to that stopping condition, then you're just never going to end. This is like saying in a while loop, the condition in your while loop has got to eventually become false, or you're never going to leave that while loop. You've got to get to your stopping condition, or you're never going to leave your recursive loop. So yeah, Tim.
Sorry to interrupt. Are there languages of like a mathematical sort of framework that they can understand that like a certain program will have an infinite recursion or an unending loop just by like analyzing the whole code's sort of Boolean values and checking to see that they all end up adding up to a condition that will end up failing?
Yes, so your question is, are there languages that can identify they're going to get an infinite recursive loop? There are some programming languages that lend themselves very naturally to doing recursive solutions. So I think of Lisp or Scheme or Racket. That's kind of a family of languages that naturally does things recursively. Prolog is another kind of language that's really naturally recursive. That's a logic-based language. There's some tail recursive languages. I want to throw Erlang into that as an example of a language that does it. But the general problem of being able to tell whether or not a program is going to stop is a very interesting theoretical problem called the halting problem. And that currently there's no known way of guaranteeing that a program is going to stop in a reasonable amount of time. So it's essentially an unsolved problem. But when I say unsolved, I mean that in a particularly nuanced theoretical way. It's a problem that people have been studying for a long time, and it's one of the most fundamental theoretical problems of computer science, whether or not you can analyze a program and determine whether it's going to halt or not.
Well, it should be a pretty simple solution to be able to say, okay, this is a for loop that goes down, that increments downward every time it runs, and it starts at 0. So that just automatically, just looking at it, like no matter what it does, it can't ever not be more than 0. So it can't ever stop. That should be something that should be pretty simple to analyze.
Yeah, so there are certainly some cases that you can imagine a solution to determining whether or not a recursive function is going to end. But even in what seems like very simple solutions or simple situations, it can be complex. So let's imagine that you just had a while loop that was while x equals true, and within the body of that loop, x never changes. So you would think that would necessarily be an infinite loop. Well, you could actually have another thread in your program that changes the value of x, and that wouldn't be visible necessarily from the code that you're analyzing. So another thread that would have a side effect that would change x. And so it looks like, just a textual analysis looks like it's going to be an infinite loop. And if you don't know anything about this other thread, you'd say, yeah, it's an infinite loop. But actually, you could have things that are changing your program that could make that not an infinite loop in practice. So there are some cases where if you make some strong assumptions, yeah, you could do it. I don't know of any kind of production level tools where that's done for you, though. I will say that there's a great plugin for Eclipse it used to be called Find Bugs. It's developed by the University of Maryland. It's now, I think it's been spun out of University of Maryland, and it's called Spot Bugs now. And Spot Bugs does some of this kind of analysis for you. It will at least warn you if it looks like you're making a mistake. And I found that to just be this really great resource for programming, because as I'm programming, it will teach me different things about programming that I maybe didn't know beforehand. It will show me how to fix it. So actually, what I want to do first here is I want to show you an example of a recursive method, period, and then one that doesn't end. And as long as we're looking at that, let's take a look at spot bugs as well, just so you can see what that looks like. So we're gonna work through this together, and it'll be a little bit of a live coding. I'm not gonna share it, or I'll share it on Saros for anyone that's online, so you can watch what's going on. Although there's not gonna be a lot of, you could watch it on the screen and it would be fine. But okay, let's see. Great. So this is gonna come up later. So here's an example, and let's just try and share this if you guys are available. And create a session for chapter 18 or for lecture 18. All right, and so what I want to do is I want to demonstrate an example of a recursive function. And so what we'll do is we'll just create a very simple static function that doesn't return anything. What's that?
Can I make it?
A simple function that returns nothing?
No, I want to make the recursive class.
We're just going to do a method for now. I'll give you a chance to do something in a few minutes. All right, and so we're going to kick this off by the main method. We'll just say recurse, and we'll give it a number to start with. Start with 10, maybe. Let that compile. And what is our function going to do? Well, it will print out the number that it was passed, and then it will call itself with one less. And then I just lost my... Wait. Come back. There we go. Sorry. Okay, so here is a method. It's recursive. How do we know it's recursive? Well, on line 7, it's calling itself. On line, is the main method recursive? One no, one yes. It's not recursive because it doesn't call itself. And it doesn't participate in a circular chain. Recurse is recursive because you can see in line 7 it's calling itself, and it's calling itself with one less than what it was initially called with. Now, this is going to create a circular chain, and hopefully it's not going to... Oh, you know, actually, since I'm broadcasting, I don't want this. Usually I would just run this and let it crash my computer if it ended up doing that. But because we're broadcasting, I don't actually want to do that.
He really wants to do it.
Crash my computer. I don't even care.
Well, let's see. Can I screen? I can't broadcast you screen share. Okay. Well, tell you what. Why don't you try and run this? And do you have it synchronized? You got something going on? Your computer crashed. Outstanding. Okay. Mission accomplished. All right, Lisa. Do you want to try and run it? And we'll just have you live stream what's happening. A bunch of numbers are being printed out.
Starting at -6968.
So that's the first one you see. It should have started at 10 and started decreasing.
And then it goes down.
Did you get a Stack Overflow error?
866, it started saying exception
Stack Overflow error. Okay, actually, that makes me feel a little bit better that maybe this isn't going to crash everything. All right, we're broadcasting. I'm going to try and run it. Let's see. We'll hope for the best here. Okay. Boom. Oh, good. That was all right. That wasn't too bad. All right, so what happened was we started printing 10, but we lost it in the buffer. The numbers got more and more and more and more negative each time we called, and then eventually we got to this point where, boom, we got this error, and there it is, our Stack Overflow error, namesake of our website that we find so appealing. If we took a look at this and we debugged this and we ran this into debug mode instead, we would be able to see those stacks start to stack up. And so the place that we need to look for that is on our stack frame. And let's see, where am I going to find that? That'll be up here. And what I'm going to do is I'm just going to hit the run button. And so we'll run again until we encounter this line in a subsequent deeper call. So I should hit run here and it'll stop again. And you can see this stack frame is where this is my first call when x equals 10. And I can bring that up over there. And then here's the stack frame. Here, I'm going to add it over here so that I don't have to keep opening that. All right, so x is 9. Here's x is 10. X is 9. If I run again, x is 8, 7, 6, 5, 4. And all these stack frames are still here. So if I wanted to go back in the call stack to these calls that haven't quite ended yet, I can go back to each one of these different frames where x had a different number before returning. But as I continue to run this, this is the stack right here that's building up. And this is the thing that's eventually going to run out of memory and crash. So that's the stack in principle. Or not in principle, that's the stack in practice. All right, so that's all well and good. This is, well, it's not well and good. This is malformed code. It's all the opposite of well and good. in all senses, it is not well nor good. It is sick and bad. We would like this to be a well-formed solution. And so what that means is we need a stopping condition. Any recommendations on what our stopping condition should be?
Return.
That would end it.
If
Now we're talking.
minus 11.
Minus 11. One person suggests 0 and one suggests minus 11. So if x, how about we say if x is less than 0, we'll do a little bit of both. Neither of you get your way. It's like politics. If x is less than 0, then we'll return.
Nobody wins.
Nobody wins in politics. But if it's not less than 0, then we'll continue recursing. All right, so in this case, we have a stopping condition. And based on the recursive call, each recursive call is getting closer and closer to that stopping condition. Eventually, we will make a call with a number that's less than 0 if we don't start there in the beginning. And so now when we run this code, we get a much cleaner result down in our console. We see that we start at 10. We make calls all the way down to 0, and then when we hit 0, we stop and we return back out of each of our stacks, each of our frames to decrease the size of our stack. Recurse 10. If we'd started 11, we would have started at 11. Make sense? You guys have seen recursion before? So far, so good. Okay. So great. That's the definition of recursion. But that's not very helpful in describing how it goes about helping us to solve problems. And so what I want to do is I want to work through an example where we use recursion in order to solve a particular problem that we might have. And the problem that I want to try and solve is the problem of creating permutations. So we'd like to use recursion in order to find all possible arrangements of a particular set of elements. And so on the right, the set of the elements that we're talking about are characters. And the set is all the characters in a string. And we know that a set is unordered, but what we would like is we would like to see all possible orderings of the elements of our set. So we want to produce all ordered permutations. So on the right, we see E, A, and T, and what we have produced is all of the possible permutations of those three letters. All the ones that start with E, all the ones that start with A, all the ones that start with T, and then once we've used that letter, all the permutations of all the things that continue after it. Okay? Problem okay? All right. Have we seen this before? A little bit? Okay. So I want to generate all the permutations of this, and the strategy that we're going to use is we're going to generate all the permutations starting with the individual elements. So we'll take each element in our set in turn, and we will consider, all right, that's going to be the first element of our permutation. Now what we're going to do is we're going to add all the permutations of the elements that remain to that first letter. So this is pseudocode. This isn't going to do exactly what we want, because I want this to represent is the fact that permutations of A and T are going to create AT and TA, and each one of those we tack E on the front, and we'll get a permutation. That's all the permutations that start with E. And then if we do that with each letter in turn, we'll end up with all the permutations of our set from the get-go. Okay? The recursion is when we do that second set of permutations here. We've, at some level, called permutations of E, A, and T, and then that smaller problem became taking the first element of our set and tacking it on to the permutations of a smaller set, the set with the first element removed. All right, so our ending condition is an empty set. And that will be our ending condition, and it will be its own permutation. And once we get to the empty set, we'll do no more recursive calls. And so we'll back up out of the stack frame. So a little slide error, repeated that animation, sorry. All right, so let's try and work through this. And we're going to do it live, and I want to do it a little bit differently than doing the permutations of the characters of a string. I want to actually take a set and consider all the permutations of the element of a set. And so in doing this, we will work with both our ideas of generics as applications programmers, also think about the way in which data structures represent ordering or unordering, and then it'll also enable us to create permutations of anything that we might have. It doesn't necessarily have to be characters in a string. All right, so let's do that. We'll drop into Eclipse here, and we'll close our example.
Possible motions.
What's that?
Permutations of possible motions.
Of emotions?
Of motions, of movements.
Give me an example of what you're talking about when you talk about.
All possible options for movements.
You mean like power moves, like up, up, down, down, kick, punch, something like that? We can do that.
I'm saying it's possible.
Well, we're going to do something, so we might as well pick something we're interested in. The only challenge is if you're thinking about it in terms of like power moves and Super Smash Bros. Or something like that, a lot of times those moves require multiple moves of the same type, so you have to do up, up. And what we're going to do is we're going to start with a set. So if we start with a set, we can only use each move one time. We could do, you know what I mean?
Yeah. Let's do.
No, words are boring. Let's the characters in a word. We could do like several. We could do permutations of words rather than characters. If we want to do that, so kind of make up sentences, sort of thing. Okay, let's do that. All right. So here's what I'm going to do. Let's see. Let's talk about how we want it to actually run for starters. So the first thing that we're going to want to do, I'm thinking about this at a high level, is we're going to want to create our input. And so that's going to be something like make a set of words that are going to be like the components of a sentence. And then the next thing that we're going to want to do is we're going to want to call the permutation generator. And we're going to want to capture the result. What is the result going to be? Well, a permutation of all the elements in the set is going to have to be a list, right? So if we took the words hello world and we said, what are all the permutations of that? Well, you could have hello world or world hello. So if we're going to get all the one permutation is a list. So all the permutations is going to be a set of lists. So here's list 1, hello world. List 2, world hello. The set of lists is the set that contains those two lists. Well, a set of lists, because each one is going to be unique. Each list will be unique. Okay? And because the ordering matters. Because otherwise hello world and world hello would be the same. Right. All right, so then we want to output our permutations. All right, so that's our general strategy. So let's start to think about let's just start at the high level, and we'll assume that these stubs exist. I'm not assuming it in the way we assume that recursion works, but I'm assuming it just because we're going to try and work through the problem starting at the top level down. So we're going to create our input. We're going to make a set of words. Okay, so that's going to be something like, we're going to need to start with a set of words. So let's make a set of strings. And this will be our, I guess we can just call it input. And we say string, not strings. And we can use a hash set in order to represent that. And we're not going to use something that we made. We'll use the Java standard hash set. That looks okay to me. I'm getting some errors. Let's see what the errors are. Okay. Which version of set I'm using isn't clear, so I want to import Java util set. That's good. And then over here, I forgot to use the keyword new to make that. And when I did that, now the parser sees that hash set is a type that I also haven't imported, so we'll import hash set. All right, so in this case, I know I have an interface called set, and I have an implementation that I'm choosing called hash set. Like, what other kind of implementation could I have used? Tree set, great. So tree set and hash set are two choices that we know about for implementing sets. Default assumption should be to use hash set because it's a little bit faster. The time when you don't want to use hash set is when you want to get your strings out in lexicographical order, the natural ordering of strings. I don't envision us needing that, so we'll use a hash set. But if we do use it, no big deal, because we'll just come to this line and we'll just change it to tree set and it'll all work because we're just using the behavior of a set. Okay, so Tim, you want to have something to do here. So let me ask you to, in these few lines, why don't you add some elements to input, the words that you want to be part of the set. And so let me undo your read-only status, give you keys to the kingdom there, and let you do that. And while you're doing that, I'm going to fill out the code below it that's going to call the permutation generator. So I'm going to say permute the input. Wait, we don't have a method for that. Don't put it there. Put it up higher. Failure. Failure, except you are creating havoc in Discord. So in that sense, it's a success. All right, and we know that what we're going to get back from the permutations is going to be a list. And what is each element of our list going to be? It's going to be a, sorry, I was wrong. It's going to be a set, but what each element of our set is going to be?
A list.
A list of strings. What? Okay. Does that seem all right? A set of lists of strings. Going deep. Okay. And then finally, we're going to need to output these. So we'll say we'll use fast enumeration for list string L in output. Gosh, sorry. So each element of our set is a list of strings. So when we enumerate over it, we're going to get one particular list of strings. And then we are going to enumerate over each one of the elements in the list, L. And we will just print out on a single line the particular string that we're working with, followed with a space. We'll put a space between. And then after we print each sentence, we'll print a new line character. Okay, so we'll let Tim add his sentences. What are we going to start with? Tim. Tim. Team. Tim is the... This is what happens.
Where's the best tip?
What is going on here?
Yeah. Tim is the best programmer ever. Okay, that's a good start. Nope, we're not done. Ever, he, ever. Ever he should. Wow, where's this going? Ever should he should teach. Never. Okay, good. That's a good input, though, for starters. So now Eclipse gives us some tools here. Because we've stubbed this out, because we've stubbed out a function called permute, and we've actually given it an input and told it what the output's going to be, Eclipse is actually going to be able to create this for us, create a stubbed out class for us, or method, and it did it right here. What was nice about that, I'm going to move it above. I like to put my methods above where I call them. So it went ahead and said, well, I see what this thing is supposed to return. It's supposed to return a set of lists of strings, and I see what it takes in as a set of inputs. And so then I'm just going to set that up for you. All right, so what we said is in order to create these permutations, we need to go through and pull one element off of our input, and we want to permute what's left in our input and add the element that we took off to what remains. Usually in recursion, when you're writing the code, you think about your stopping condition first. So let's add that. So we know our stopping condition is if we make a mistake and we say input equals null, so that's just to make sure we don't have malformed input, or input.size equals 0, then we want to return just a set of lists that have nothing. So new hash set string, new hash set list string. Okay. So if we get down to the bottom and we get to our ending condition, we're going to return an empty set of lists of strings. Got nothing in it. Good? Now, I hope the error that it's telling me is that I'm not returning something in all cases, because if I don't meet this condition, I'm not actually returning something. So let's make sure that's what our error is. Great. It says this method must return a result, and in some cases we're not. So the more general case, when we're not at our stopping condition, what we're going to want to do is go through each element of our input and take it off, and then take what remains. So let's see, how do we want to do this? Let's make a fast enumeration. So we'll go through each element in our input, and we will create a copy of our input. And so let's make a set of strings, which is our copy. And that's going to equal a new hash set string. And what we're going to initialize it with is our input. So this, again, gets around the problem that we looked at 2 classes ago about our references pointing to the same thing. We actually want 2 different sets. And so we're not going to just say copy equals input, because then there would be 2 references to the same thing. Instead, we're going to ask the hash set constructor to duplicate a shallow copy, but that'll be good enough for us here. So now we have one element from our input, S. We have a copy of our input. Let's remove S from our copy. How does remove work? Well, it removes the specified element from this set if it's present, and great. And it looks like it returns returns true if the set contained the element. All right, so we don't really care because we know that that element is going to be present because we just created a copy. But what is left over now is copy, and actually I'm going to call this, I'm going to change the name. I'm going to call this the smaller set, because it's going to be the same as our input, but it's going to be slightly smaller. And I'm going to not keep doing that. There. All right, so that smaller set is what we want to create our permutations over. So we'll say solution equals the recursive call on the smaller set. We're going to ask for all the permutations of the set without one of the elements. We haven't declared solution, and so we need to make sure that solution has the right type. And what we're going to get back is a set of lists of strings. We've taken off S from our input. We've gotten back permutations of the set with everything but S, and now we need to attach S to the front of each one of those lists. So having gotten our solution back, we will do a fast enumeration over our set. So each one of our solutions are permutations, call it permutation, over our solution. And let's call it solutions since it's more than one. And in each one of those lists, we want to say permutation dot add, and we want to add it to the beginning. The way lists work is they add it to the end, but we're assuming adding it to the beginning. So we're going to have to use the version of add that has an index. So we say 0 and S. Boom. So we'll go through each list, we'll add something to the front of it, and we don't need to change our solutions because solutions is a bunch of references to lists. So once we've done that and we've looked at all of our possible inputs, we can just return solutions. Well, let's see. Actually, that's not going to work. We're going to have to combine all of our solutions, right? So this is just going to be the solutions that start with S. So we're going to have something that looks like all solutions. I'm putting it outside the loop because we're going to have to collect all of our solutions from all the different starting points. All right, and I'm going to do a little trick here. Okay, ready? Watch this. I'm going to optimize my code. I'm going to put the all solutions right there, and I'm going to return all solutions, which is going to be empty otherwise. See what I did there? I need all solutions no matter what. If I'm at the ending condition, I'm going to return the empty set. Otherwise, I'm going to come down here. After I've created solutions for the smaller problem, I'm going to say all solutions dot add all solutions that I just calculated. Okay. Looks a little baffled. So and then at the end we're going to return all solutions. Let's make that error go away. All right, now we're gonna have to take a look to make sure this is doing what we intend it to do. But what I intend to happen here is we call permute. Line 10, we create a holder that's going to have all of our permutations in it. It's a set of lists of strings because one permutation is a list of strings. Line 12, we make sure we're not at our ending condition. Our ending condition is when our input has no elements in it. Line 16, we go through each one of the elements of our input and we pull one off. So S is the one element we're pulling off. When we pull that element off, we need to get the smaller set that we can work with for our recursive call. So we create a copy of our input and we remove the one that we pulled off. That's line 17 and 18. Line 20, we make our recursive call and we just assume that if we permute on the smaller set, we're going to get back all the permutations of the smaller set, a set of all the permuted lists. We'll go through each one of them. We'll tack on the element that we removed to the front of it. And once we've done that, we'll add all our solutions to our aggregate variable. I feel like I just said what I said before, and that didn't help at all. But okay, well, that's good. So then we get down to the end here, and we should print it out, and that should be okay. I don't know how this is going to go. Tim is the best programmer ever. He should teach this class, is a lot of words. And so I can imagine that's going to generate a lot of permutations. Can we do... what I'm going to do is I'm going to reduce this briefly just so that we can check that it works without generating a ton of output. So we'll just go through here real quick and we'll start with maybe Tim is a programmer. We'll start off a little bit more modestly and see what happens. All right. If that works okay, let's see if we can pull it off. Run permutations. All right, well, something didn't go well. So much power. Last time I gave you write access. All right, are we still running? I'm going to check debug. Nope, the program ended. It didn't end up printing anything out, so something didn't go well. I'm not sure what it is, but the only way for me to figure this out is to walk through it and see where we made an error. So I'm going to put a breakpoint here, and then we'll try and run debug. We'll debug as a Java application. Okay, switch to debug mode, or debug view. So line 31, we create a new set called input, and if all goes well, we will step over that line, and we'll get 1, 2, 3, 4 elements into our input. Do we look like we have that? Yep, we got a programmer Tim is. So you can see that it's a hash set, so the ordering isn't preserved because it's a set, and using its hash codes, it ends up with that. Okay, so now we're about to call our permute function, so let's step into that code. Our first call, we create a holder for all of our solutions. What is input right now? Input is that set, so that looks okay. So is input equal to null? No. Is input size equal to 0? No. So we should end up stepping over that. Good. So now we're going to walk through each one of our strings. So the first string S should be A. Okay, so S got A, that's right. Now we're going to create a copy of our set, smaller, and smaller should have all the elements that input has in it. Good, does. Now we're going to remove the A from it. Good, we got rid of A from smaller, and A should still be an input. Good. Now we're going to make a recursive call on the permutation, so let's step into that. Now we're in a second version of permutations where now input has everything but A. So we'll step over that. We believe all this is working so far. So now we're going to step into the second call to permutation. Boom. Now input has everything, only has Tim is left. So we'll step over the beginning code. We'll remove S, which is Tim. We'll now step into our recursive call. Now our input is just is. And so we'll walk through this. Now we create a smaller set. We remove the one element from our set, so smaller should have nothing in it. Good, it has nothing in it. We're going to step into permutation now, and input is now empty. We're going to step over this. Our size should be 0. So we're going to return all solutions, which is also empty, because this is our stopping condition. So I'm going to step over this line, and we're going to return back to our previous call where input consisted of just the word is. Now as we step over this, we're going to walk through each one of the lists of strings that are there. Okay, we didn't actually create an empty list to start from here. So we created a set, but we didn't put any empty lists in our set. So we don't actually have any empty sets to add our permutation to. So if we step over this, this is going to skip this step because we didn't have any empty lists in there. So we're going to return a solution that we didn't actually end up adding anything to. So we'll run out of that and come back and I'll show you what we didn't do. Here, when we get to our stopping condition, we have a set called all solutions, and our set doesn't have anything in it. We need it to have an empty list in it so that we can prepend stuff to it. So instead of just returning it right away, we're going to say all solutions.add a new list of strings that has nothing in it. This is like in the example of, sorry, we need a particular implementation. What do you want? Array list? We want array list. This is like returning an empty string, except we're returning an empty list. Let's save that. Compiling OK. Let's run it. Boom, there we go. All right, so what are all the, it's kind of curious because they have the same number of characters and because this is a fixed width font, it ends up looking blocky, but we're getting all the possible sentences. Programmer Tim is programmer Tim A is programmer. Is Tim a programmer? Tim programmer A is. And none of them are actually duplicates. It's hard to see the pattern here because they're all, mixed up. They're not starting with, because we're keeping track of it in a hash set, we're getting all kinds of different solutions. So what if we switched it to be in a tree set? Not sure that's quite going to be enough to do what we want to do. We'll keep our input doesn't have to be a tree set. Good. All right, let's try that. What did I do wrong? Oh, no. This is, yeah. Okay, this is a little deeper than I want to go. So we'll just send it back to hash set. The problem is that for something to be in a hash set, it has to be comparable. You have to be able to compare two things so that you know which one's coming forth first. What? In a tree set, what did I say? In a tree set, things that you put into them have to be comparable, and an array list isn't comparable. You have to, so it didn't work from the get-go. So what I'm trying to do, though, is I'm trying to sort these. So what if we said the linked list is also not comparable?
Oh, really?
Yeah. You would have to decide what it means for one list to come before another list in order to do that. And so you would have to create your own class that would be like a comparable array list, which is not hard to do, but you have to decide what it means for one list to come before another one. I still kind of want to see these things in order, but that's going to take too much time. We could, but too much time for now. Nice result, I think. We see all the different possible sentences containing the words that we started with, including the one that we began with, which is Tim is a programmer. Somewhere in here we should see that one. Tim is a programmer. Great. But now if we went back and we tried to do what the original narcissistic impulse was, I know it's in the water, right? Well, it's sort of, if you're not narcissistic, you're not anything these days, right? I didn't call you narcissist. I said that impulse was narcissistic. I just ran it again. It's taking a long time. It's taking a long time because there are a lot of permutations. I'm a little bit scared because it's possible that we could get a Stack Overflow error just because there's actually too many permutations, not because it's a mistake. All right, and I'm getting nervous, so I'm going to stop it. Let's see. Let's try it with one additional line at a time. We know 4 worked, right? So let's try 5. So Tim is the best programmer. That's a good start. All right, that was pretty easy. Best programmer ever. That worked okay. There we go. That's pretty good. Oh, that might be enough. That's going to be enough. Teach ever is Tim should best programmer the he. All right, now here's the thing. We just wrote a permutation algorithm that's completely agnostic to what is actually being stored in it. We could have made a set of anything besides strings. Because we're using generic classes and because our permutation doesn't care what's in it, up here, well, that's not true. Our permutation actually did use a specific type. Let's make it generic so that we can use any type we want. To make a generic method, we have to say, okay, well, let's declare the generic type that we want to use. Fine, that makes it a generic method. Now let's go through in all the places where we use string, let's change it as appropriate to T. Okay? So now we just made our permute method be completely agnostic to the kind of type that we're permuting. This is our implementation, but when we actually use it, we have to actually store something specific in it. If we do that, I'm going to make it a little faster. It should still work. There it goes. He best ever Tim programmer should that is. And thwarting you in that attempt right there. We could then make it a different kind of input, right?
You should probably delete the slash at the bottom.
Let's try, hold on a second. Let's try doing all possible permutations of a set of integers. So this could be, for example, maybe you have a, maybe you have a code, like a lock, and you need to come up with all possible combinations to try. Now we're able to permute all possible numbers, except that I have some kind of error in my system. Oh, because my output is no longer strings. It's integers. Okay. There we go. So now, instead of permuting all possible combinations of strings, we've made permutations of all possible. We made all possible permutations of the numbers there. All right. I think that's a pretty elegant darn solution. We've made a generic method that takes in a set of elements of any type. That could be characters, that could be strings, that could be some class that you've defined. And without knowing anything about what you have a set of, you create all possible results coming out using just data structures and generic types. I think that's nice. It's so nice that I think we should take 5 minutes and just dwell on how nice it is. And so we'll take a 5-minute break now to stretch, and we'll come back and look at a next challenge with recursion. All right, back in 5. Yeah, just okay. All right, Philosophy 101 during the break, and we are back. And what we just walked through is the example of permutations and looking at a generic method, both in syntax but also conceptually, that would take any references and form all combinations of those references, provided that you started with a set of them. So this was a recursive solution, and it's a solution that is pretty well represented as a recursive algorithm. It would be difficult to imagine how you would go about doing this iteratively with like a for loop or a while loop. It is very hard to think about that because basically, like the slide says here, is that an iterative solution would have to have some kind of a loop, right? So a while loop or a for loop. And each time you go through the loop, you want to create the next permutation of your set. But there's no obvious way of getting that next permutation. For example, if you already went through and you had EAT and ETA and AET, how would you figure out what the next one is? Because the whole point, of course, is to figure out all the permutations. So you don't already know it, and somehow you have to, in the next loop, generate the next one. Now, it's not that this is impossible to do in iterative loops, because all recursive solutions and all iterative solutions, you can solve everything you can solve recursively in iteration and everything iteratively in recursion. But it's not exactly, it's not a program that naturally maps to iterative solution. It's a program that pretty naturally maps to a recursive solution, if you've figured out how to think recursively. If you think about permutations as being, well, I'm going to take the first element off my set, and I'm going to find the permutation of everything that remains, and then tack it on the front of the things that come back. If you think about it that way, well, then it naturally works that way. It's hard for me to even think about an iterative solution, although I know they do exist. All right, this is a solution for permutations. The next one I want to look at is a solution for a problem called mutual recursion. I think this is super elegant as well. I think we touched on this in CS-10, but we went over it really quickly in Python. Do you remember talking about solving expressions recursively? Yeah, we did it really fast. What I'd like to do is spend a little bit more time on this one, and then what I would like to do next class is to do a solution, a Sudoku solver, because a Sudoku solver has a lot of the same properties as combination of the permutations and the mutual recursions. And it's kind of a general example of how you might solve any game system by examining possible solutions and then backtracking. The formal term for it is backtracking, we talked about in the textbook. But okay, so in mutual recursion is an approach. It is an example of a circular recursion rather than just a function calling itself, like permute. Mutual recursion involves multiple functions calling each other in a circular pattern. And so you create a cycle of calls that are recursive, but no individual method is recursive. And so that mutual recursion is the technique. The problem that we can solve with it is the problem of evaluating expressions. So if you imagine that someone types in textually the expressions 3 plus 4 times 5, or decides to put some parentheses in there, 3 plus 4 times 5, how you evaluate those is going to be different. So in the first case, because of the order of operations, 4 times 5 is 20, and then we add 3 to it, and we get 23. But in the second bullet, the parentheses take precedence over the multiplication, and you do 3 plus 4, get 7, and multiply it times 5, and get 35. So depending on where you put those parentheses, you're going to get different answers because of the order of operations. And we can use mutual recursion to parse this sentence, this algebraic sentence, and deliver a particular answer to us. And we need to respect the fact that there are these orders of operations that we want to work with. The way we're going to tackle this is by using mutual recursion. So if this diagram comes from our book, and what it is it's a visual representation of the grammar that we're going to use to represent an algebraic equation, an arithmetic expression, not algebraic. There's no variables. And it's going to consist of three different components. And if you look at that, you can see that there's a circular expression going on. So the way you read this is you see at the top level that an expression is either just a term, or it's a term followed by a plus or a minus and another term. So you could have a term plus a term plus a term plus a term, or term minus a term, term plus a term minus a term, as many as you want. You can go through that circle as many times as you need to in order to parse an expression. And eventually you have to leave the expression having either seen a term or a sequence of terms. What's a term? Well, this is the second breakdown there. So a term is going to be composed of factors. I don't know what a factor is, but a factor is a number of things that are, a term is either one factor or it's a factor with a multiplication and division separating it. Well, what's a factor? Well, a factor is a parentheses surrounding an expression or a number. Number just being a digit or a sequence of digits. Well, what's an expression? Well, an expression can be a term. Well, what's a term? A term can be a factor. Well, what's a factor? A factor is an expression in a term. So you can see that in this grammar, there's a circular sequence. There's a looping pattern. But you can also see that there's something that's happening because it's not just an expression, so it can't go on forever. It's an expression inside parentheses. So we can take this grammar, and if we have a well-formed arithmetic expression, and basically that means that we only have digits, plus, minus, times, divided by, and balanced parentheses. If we have that, then any arithmetic expression can be parsed using this expression term and factor grammar. So let me give you an example of two of them. So at the bottom, we see the two expressions, the bottom of those trees, we see the two expressions that we introduced in the bullet. So here and here. And you can see that by adding those parentheses, we get a different, what's called a parse tree. This is a little bit like you might, if you in English, if you had kind of a traditional elementary school education, you might find yourself parsing sentences and identifying the different parts of speech in a sentence. It's kind of rare these days, but given the propensity for classical education at Westmont or homeschool, you might actually encounter it. This is like that, but instead of parsing it according to a sentence tree, we're parsing it according to that grammar that we just made up. So if we start over on the left, we can see that each one of these things, the only way it can be consumed by that grammar that we saw previously is, well, each of these has to be understood as a number. So this is going to be filled in as a number, and a number. Well, the only way that a number can be understood, if we go back one, a number can only be understood, you can't loop in the factor. So the factor has to translate to a single number or an expression, and then you have to go up the tree. So, well, if you have a factor, then it could be a term. And that term could be a factor, and that factor could be a number. But if it's going to be a number, then it has to be surrounded by a times or a divided by in order to get another number. Well, it's not. It's got a plus sign. So it can't be a factor times another factor. We've got to go up another level and say, well, this factor has to be understood as a term. So we had down here at the bottom, we had that 3. This factor was a 3. This term was the 3. This expression was the 3. Well, now we can combine that with the plus and minus and say the expression was a 3 and a plus and another term and another term. So we come over here and we can see that the expression is a term plus a term. And recursively, the term was a factor, and the factor was a number, and the number was 3. This term was a factor times a factor, and this factor was a number, and this number was 4. This is a unique parsing of that sentence. There's no other way to parse this sentence according to the grammar that we put in place. And that's important because this tree represents a way of actually evaluating the expression. We go down as deeply as possible before we evaluate what's there, and the result comes back up in our expression evaluation. So this branch of the tree evaluates to 3, and this is a 3, and this is a 3, and this is a 3, but then we have to stop because we need the other branches of the tree in order to evaluate this expression. Well, this term can't evaluate that yet. Evaluate this factor, it's a number, it's 4. So the 4 evaluates back up here. 4 times factor, factor is a number is 5. So as we back up this tree, we get 4 times 5. This term evaluates to 20, and now we get 3 plus 20, and this evaluates to 23. Now when we throw in our parentheses over here, we can't parse it the same way because these parentheses have to be consumed by our grammar tree. And we know that the only way to consume parentheses is for it to be a factor as a parenthesis and an expression and a parenthesis. Well, now we have an expression. Okay, this is easier to understand. It's got to be a term plus a term to consume that plus. The term is a factor. The factor is the number is 3. And now, and we get the same thing on the right with times a factor and a number. We always start in each case with the root being an expression. And now when we want to evaluate this expression tree, we have to go all the way down that evaluates to nothing, that evaluates to nothing. This evaluates to 3 plus 4. This evaluates to 7. This becomes 7 times, go down here, this evaluates to 5. 7 times 5 is 35, and then we return up and we get 35. So two expressions, very similar. Difference, the only difference is the parentheses, but the way we consume those parentheses is dictated by our expression, which changes the result along the way. So what we would like to do then is we would like to write some code that reflects this way of consuming our expressions and evaluating our functions. So it's mutual recursion, so we're going to have several different methods that are working together. They're working cooperatively in order to parse this. And so in order to compute this expression, we're actually going to have 3 methods that map very directly. We're going to have one called get expression value, one which is called get term value, and one which is called get factor value. And what they're going to take as input is a sequence of characters in the string, and what they're going to return is the evaluation, the numerical evaluation of those characters in the string. Comments or questions so far? Okay. All right, so let's take this idea. In this case, we're not going to live code it. It's a little more complicated than I feel comfortable doing on the fly. So what we're going to do is we're going to look at the code, look at a solution, and then we will just walk through the different steps that are involved. Okay? All right, so if we jump in, no, I don't want that. Thank you for offering. Again, terrified of its own way. All right, so we have 3 different methods that we're working with. We're working with expression calculator, expression tokenizer, and this mutual recursion class. So where we start is we start with expression calculator, and this is the function that is the application program that uses these different classes. So expression calculator has one method, which is main, and we create a scanner class, and what that does, if we pass it system.in, is it asks for input from the console. So it allows the user to type in an expression. This isn't actually asking for it, but this is just setting it up so we can take it. In this line 15, we output to the console a request to the user to please enter an expression. Then in line 16, we take in an entire line of text that the user types in. We then pass that line of text into this object that we're making. So we're creating a new object called mutual. It's a constructor, and into the constructor we're passing the input. So mutual is going to do something with that input and return back a mutual object, and we're giving that reference, we're going to call that E. E is going to be a reference to that object that we create. We don't know much at this point about what mutual does, but apparently because of line 18, let me switch this to integer. Because of line 18, we see that one of the things that you can do with the mutual is you can call get the expression value. And based on what we just saw in the slides, you can assume, and then we're going to see that in a second, what it does is it goes through and it consumes all of the input, assuming it's an expression, and returns the numeric value of that. So at this level, it's a very abstract and encapsulated approach to solving this problem. Here's a class, give it the expression, it'll give you back the result. At a high level, that's kind of what we're asking for, right? How does it do it? We don't really know yet. It's abstract. There's an implementation there. We're going to dig into it. But at this level, we just say, okay, well, here's the input that I got from the user. Now here's the equal sign. Here's the value that I got back as a result. Add some spaces there. All right, and then the last thing we do is, regardless of what happens in this code, if we get an error or anything else, we're going to try and close our scanner just to have good code hygiene. All right, so let's just run it at a high level and see if it does what we expect it to do. I hope it does. All right, so down in the console, we're saying enter an expression. Lisa, you want to dictate an expression off the top of your head to me?
Plus 2.
Okay. I don't know. I think that's just going to fail because this is an integer solution. Well, it really should be, right? We should probably fix that. Let's in the context of this code, let's go through and actually make it so it does the correct thing and returns a double. we're not going to be able to do it at this point. So let's say, let's add some parentheses in there. And we know that 2 times 10 is going to happen first. So whatever we get in the parentheses needs to divide 20 evenly. So 4. So 1 plus 3. Okay. So if we believe, let's calculate, let's like do a little mental test. If we believe that is going to be evaluated correctly, belief nothing. If that is evaluated correctly, what's the answer? We'll use order of operations. So the first thing we're going to do is parentheses, so that'll be 4. And then we go left to right with times and divided by. So we'll get 2 times 10 is 20. Divided by 4 is 5. So 5 plus 5 will be 10. Well, let's see if it works. Okay. And it did it. Answer's 10. All right, so let's see how we went about doing that. So let's start by looking at the constructor, since that's what we're calling here. So I'm going to put my cursor there, and I'm going to hit F3 and go to the definition of that constructor. And you can see that when we construct this evaluator, what we're doing, 9, when we construct that when we construct this mutual recursion object, what we're doing is we have an instance variable called tokenizer, and itself is some kind of a class called an expression tokenizer. So what this class is doing is it's breaking down our string into the component parts. So each token in our expression will either be a number or it will be a character that represents an arithmetic operation. And we're going to be able to walk through that expression tokenizer and pull things off one at a time. And the reason why we're creating a class to help us out like this is because sometimes digits are more than one character, and because we have spaces in our we could have spaces in our input expression as well. Okay, so we've got this expression tokenizer, so let's actually dig into that and see what an expression tokenizer does. All right, we can look and we can see here are the things that our expression tokenizer allows us to do. We can construct one with a string, and then what we can do is we can peek at a token, or we can ask for the next token. So this is going to take chunks off of our string in ways that are meaningful, either digits or operators. All right, so when we construct an expression tokenizer based on a string that someone has typed in, so for example this down here, we're going to start by setting an internal instance variable equal to that string, and we're going to start some kind of pointers called 0 and set start and end equal to 0. And then we're going to find the first token. So we're going to call a method that's publicly available, but we're going to call it from our constructor. So if we look down at next token, what is next token going to do? It's going to get the next token and move the tokenizer to the following token. All right, so it looks like what we're going to end up doing is taking the first token off, but this is probably an initialization step. All right, so we're going to look at what the first token is. All right, this is a little deeper. I have to look at peak token. If start is greater than or equal to the input length, then we're going to return null. So what it appears like we've got going on is we've got a start and an end that's bracketing the parts of our input that we've looked at so far. And if start moves off the end of our string, then we're done. We're done consuming tokens, so we'll return null. Otherwise, we're just going to take the chunk of our string between start and end. So start and end are just going to move down and grab the different pieces of our string. Peak is just going to tell us what comes next, but what next token is going to do is it's going to grab what comes next and then advance start and end. So we'll grab the thing that comes next, that's R, and then we'll move start to where end was because we just consumed something between start and end. And now we're going to walk end down until we get to the end of the chunk we could consume. All right, so if start is greater than or equal to our input length, then we're done. There's no point in doing anything else. We'll just return the thing that we grabbed, and that'll be the last token we get. But if we have more characters to consume, then we're gonna increase end one time for every digit that we encounter. So we're going to look at the character input that's currently at our start position. And we're going to say if what we're looking at is a digit, like 0 through 9, then we're going to say end is increased by 1. So that means that the first time we encounter this, we will move end over a particular character. If it's not a character, then it must be one of our mathematical symbols. And so we're going to increase our end position to be one character away so that start and end only differ by 1. And so start and end will only deliver one character, and that's going to be the times, the plus, the divided by. But if it turns out that we're looking at digits, we need to keep walking our end forward. We need to keep adding 1 to end until we get to the end of our digits. Okay, so that's just to make sure that if we have multiple digits in a row, we capture that whole thing as a number. All right, so that breaks up our string into tokens. Each time we ask for next token, we're either going to get a string, which is a sequence of digits, or we're going to get a string, which is a one-character mathematical operator. And we're going to store that object, that behavior, in tokenizer so that we can call it when we need it. All right, that's a little bit of the abstraction. That's just setting us up. So if we go back to where we started this all from, equation calculator, that was just the constructor. All that is doing then is it's setting up some behavior so that we can get tokens from our expression. Now when we actually want to calculate our value, we're going to go deep into expression value, and this is where our parsing happens. So an expression, because of what we saw in our grammar, an expression must start with a term. Right? See that in our diagram? An expression must start with a term, so the value of our expression is going to begin by getting the term value. Now we have this tokenizer, so the tokenizer is where the strings are going to come from that we're evaluating. So we get term value. Okay, that's a recursive call. Here's get term value. Well, a term starts with a factor. Term's got to be a factor. So the first thing that we do is we consume a factor. Okay, well, what's a factor going to do? Well, a factor, whoa, that go away. Hang on, does that mean we just stopped broadcasting? Nope, we're still broadcasting. Good. Wizard of Oz just revealed himself. All right, so when we get a factor is either an expression in parentheses or a number. So what we're going to do is we're going to take a look at what we've got, and we're going to say, let's peek at our next token. If our next token is a parenthesis, then we're actually going to consume that. We're going to call next token, and that's going to walk start and end down 1. And that would return the parenthesis, but we're just going to throw it away because there's nothing to do in terms of evaluating it. And if what we saw is a parenthesis, then the next thing that we're going to do is we're going to pull an expression off of the bit in between. And then when we're done evaluating that expression recursively, well, the next thing is going to be a parenthesis if it's a well-formed expression. So we'll just consume that and be done. And what we're going to return then is going to be the value of the expression that was between the two parentheses. So down here we return it. If our factor was not an expression with two parentheses, then it must be a number. And so if the next thing that we looked at wasn't a parenthesis, then it must be an integer. And we're going to take the next token, which is going to be some sequence of digits as a string, and we're going to call integer.parseInt, which is going to turn those strings into an integer. Yeah, so that's going to be a problem in our grammar, because in our grammar we don't really have support for doing negative numbers. We don't have support for scientific representation of numbers. We have a limited grammar. So if we try and represent a negative number, our grammar is going to interpret that minus sign as a subtraction, and it's not going to parse. So that's a good observation. We could, in theory, we could add that to our grammar if we wanted to, but it would take a more elaborate evaluation or another recursive call. What I'd like to do is I'd like to add another operator to this code, but I want to do it. I want to add a different operator rather than adding a different way of parsing the number. Okay. If it does just turn out to be a sequence of digits, then we're going to capture its value by converting those digits into an integer, and we'll return that. So the result of calling get factor value is going to be a number no matter what. It's either going to be the raw number that we just parsed, or it's going to be a number surrounded by two parentheses. And this is the recursive call, the mutually recursive call. So get expression value forms another recursive loop. But the reason why this is likely to be well formed is because we consumed some of the tokens in the process of calling get expression value. We pulled off a parenthesis at the beginning. So our problem must be getting closer and closer to a solution, or to the stopping condition. This down here being the stopping condition. When we encounter a number, we don't make any more recursive calls. We just evaluate the number and we return that back out. When we return from get factor value, and we were doing get term value, well, we evaluated something. We have some value, and we know that a term can be a factor, but it can also be a factor followed by a times and a divided by sign. So we have to check that out. We have to say, well, if we assume we're not done, and so while we're not done, we're going to take a look at the next token, and if the next token is either a times or a divided by, we know we're in a situation where we need to consume another factor. And so we're going to pull off the next token, which is going to be the times or the divided by, and then we're going to get the next value in our sequence of multiplies and divides. If it was a times, or if it was a divided by, then we're going to go ahead and combine the values that we get. And so we're going to convert from our string representation into our numeric representation. And we will continue doing this loop until we no longer encounter a times or divided by. And that's going to match our grammar. Meanwhile, in an expression, we're going to do the exact same thing, but we're going to use our times and minus and continue combining things with pluses and minuses until we no longer see a plus or a minus. Eventually, we'll be finished consuming terms, plus and minus, and we'll return that value. So you can think about this as trying to consume all the different tokens that are in our input string from the beginning. So then when we end up running this, not that one, when we end up running expression calculator, we get a nice solution, whatever we've got. So let's add another expression to this. Oops, sorry, it's not quit yet. Let's add another expression to this. And we know that right now we can't support, what we do support is plus, minus, times, divided by, and parentheses. What is another operator that we could support that has that has something on the left and the right? So binary operator. So another kind of mathematical operation that we could add in here. Well, like Tim's definition of like a minus sign only has something on the right. It only operates to the thing on the right, whereas plus has a left and a right side that we combine together. So to do this in a reasonable amount of time, we need to just extend it with a binary operator, something that has a left and a right side. We know some because of the syntax of Java. So Java's got a handful of other ones we could use. They've got to be numeric too because we're doing arithmetic expression. Okay, mod. So we take a left side modulo a right side, and so what's our operator for that? Like what's the character we're going to use? Okay, typically we use a percent sign. We can use a percent sign, but this is our language, so we could actually do anything we want if we don't want to use a percent sign. Okay, for clarity, we'll use a percent sign. Off the top of my head, I don't know what the order of operations is for the percent sign with respect to plus, minus, times, and divided by.
Wouldn't it be the same as division?
I don't know. I mean, it's formally defined. You can look it up in the Java specification. We need to decide, when we implement this, we need to decide what it is that we're going to have it be, though.
Let's make it the same as addition.
Well, if it's the same as addition, then what we'll end up doing is we'll just put in another jobber right in there. So we can do modulo. If we want it to have less precedence than addition or higher, or it sit in between precedence, then we're going to have to add another function. But fair enough, we can do just put it in the middle, put it at the same order of same precedence as plus or minus. So what we're going to do then is we're going to add a condition that goes right in here. Okay, so let's take a look at our code. And okay, so that means that in our get expression value, we don't just have plus or minus, we also now have another operator, which is the modulo sign. So if it equals plus or minus, or it equals the modulo symbol, percent sign, then we're going to discard the plus or the minus or the modulo. We'll get the next term value, and if it equals plus, then we combine the values with plus. But if it equals minus, then we're going to combine the values with minus. Otherwise, the only thing we know left is modulo. So we'll say it's going to be value modulo value 2. So now we've just added a whole nother symbol to our grammar. And if we run our code, and we run the right code rather than whatever I just ran, we should be able to say what is 20 mod 2, and that should be 0. Cross my fingers. Boom. We run it again, we could say what is 20 mod 1, or mod 3. So what should that be? 20 divided by 3 goes in 6 times. That'd be 18, so remainder 2. That should be a remainder of 2. Boom. Run it again. Let's do it. Let's put in some parentheses. So let's say we know multiplication has a higher order precedence than modulo. Let's just make sure that's true. So if we said 4 times 5 mod 3, that should be 20 mod 3, so that should be 2. Buy that? Okay. Worked out. Okay, what if we do parentheses? What if we said 4 times 5 modulo 2? So we think that the parentheses should be done first, and so within the parentheses, 5 mod 2 is 1, so that should end up being 4. Pretty good. Let's go back. Let's add something else. What else could we add? The what? Floor division. So I think we're actually doing floor division already. Do you want to? Let's set this up so that we're doing doubles instead of integers, so that our division isn't floor division. It's actually the right thing. Okay. So that means that way down at the bottom, at our ending condition, rather than parsing an integer, we're going to parse a double. And what we're going to get back is going to be a double. So we better say our value is going to be a double. And we're not going to parse int. We're going to parse double. Let's make sure that works. Great. All right. Now we are going to return a double as well. And this line 42 is giving us an error because a get expression value doesn't return a double yet, but we're going to fix that. Okay. Let's fix that one. So we know we want it to return a double. And so whatever term value is going to return should be a double. Come down here, and we think, okay, the value is going to be term value. That needs to be modified to do a double. But if we do a double plus a double, that's going to be okay. We're going to run into some trouble if we try and do a double mod a double, right? I'm not sure if double mod double is defined.
Let's see.
Yeah, we'll find out. Let's fix get term value. Factor value. That's all good. So now this divided by should give us a floating point division. All right, expression calculator assumed that what we were getting back was going to be an integer, so it's not. So now let's see. So the other thing is that we don't, when we tokenize, we're tokenizing based on digits, and if we want to be able to represent a floating point, we need to also consume that floating point, right? So our tokenizer, we need to come down here where it says, okay, if the character is a digit, well, or if it's a decimal point. This is getting a little risky. Okay, I'm a little bit nervous because I'm now flying by the seat of my pants again. All right, so if it's a digit, or character, or the input character at start All right, let's see if I can figure out what's going on here. Cannot invoke equals string on the primitive type character. Okay, so we'll say equals period. Okay, if it's a digit or it's a period, balance our parentheses, then we want to increase our tokenizer by 1. Now this isn't gonna be a perfect parser because this means that we could put multiple periods together and that would be acceptable, but for now we'll say it's okay. So while the end is less than the input length and character is digit, or okay, or it's a period, okay, then we want to increase the ending condition. I think that's going to do it. So if we run and we just say, okay, let's just see if our parsing works. Okay, 1.0 equals 1.0, that's good. Let's see if 1.5 equals 1.5. Oh, that's not so good.
Oh no.
Yeah, that's
The problem.
so that's a problem when we evaluate our number. So we come down here and we say parse double tokenizer equals next token. So let's just, as a little bit of debugging, let's just make sure that we're getting the right thing out. Let's capture our next token, and we're just going to output to the console what it is that we see here. Okay. All right, let's just do that to see if we got the right thing from our tokenizer. Oh, sorry, typed in the wrong window. All right, so our tokenizer didn't give us the right thing. So somewhere down in our tokenizer, we didn't actually do the right code here. So let's see. If character is digit or input at character start equals a decimal point, then while we are less than our input length and it is a digit or it is a decimal point, then increase it. So something is not working right here, and I might have to abandon this effort, but it seems like that should be correct to me. So let's put a breakpoint here and try and debug and see if the parsing is going correctly. So enter 1.5, switch to debug mode, go to where we broke. All right, so now we can look and see what is our input. 1.5, what is our start position? 0. Okay, so we'll step over that line. End is now 1, so we have 1.5 as our input. Our next token would be the 1 character. So if end is less than input length, it is, and character, oh, I see that bug. Here it is. Shouldn't be start, it should be end. Boom. Okay, now it's going to work. Okay, 1.5. Boom, 1.5. All right, so now if we do 1.5 plus 1.5, 3, nice, and we have our debug there. Let me get rid of that debug code. All right, and so now we don't know what's going to happen. What if we do 1.5 plus 1.5 mod? That's going to be 3, so mod 2. 3 mod 2 is 1. That's actually pretty good. Wow. I can't believe the power of what we've just created. All right, what if we did 1.5 plus 1.5 mod 1.5? Well, that's right too, because the remainder is 0. Huh. What is even happening? This is so effective. Nothing is this effective in my life. Okay, well, 2.5 plus 1.5, that's 3, that's 4. 4 mod, say, 0.7 shouldn't be clean. Oh, I bet that's right. Is the remainder of 4 divided by 0.7? What? Ask Siri. What is 4 divided by 0.7?
It's about 5.7142.
Oh, no, that's right. Remainder is 0.7. Wait, no, that's so wrong.
So 4 divided by 0.7. Yeah, I guess I don't know what the definition is of mod when you have doubles, because it's not clear what the remainder is, because a double divided by a double is a double. There's no remainders. Yeah, so we'll have to look that up a little bit. But clearly there's a definition because we're just asking for it. So, wow, that was remarkably effective. Teaching win right there. So, okay, in summary, what is it that we tried to tackle today? We tried to look at recursion, and because up till now what we've been doing is we've been looking at we've been looking at the syntax of the language and how we can represent data, represent it as array lists and represent it as classes and think about generic types. And recursion is a little bit different. It's about how we can use these structures in order to solve problems. One thing that we looked at was permutations, and the other one we looked at was mutual recursion. Permutations involved a method calling itself, real simple definition of recursion. The expression evaluator involved a circular call of expressions calling each other, a more complicated definition of recursion. Both of them were well formed because they had stopping conditions when we ran out of strings to permute, when we ran out of characters to consume, and both of them, as you recurse, came closer and closer to that solution by either reducing the size of the set you were permuting or consuming tokens in the expression evaluator. The expression evaluator actually turns out to be very powerful. I kind of surprised myself with it. By adding additional operators to the plus and minus, adding the mod to that, we could easily add something that had the same order of precedence by adding another condition in that term evaluation. If we wanted to add something that had its own order of precedence, for example, somewhere between plus and times, we would have had to add an entire new function to our mutual recursion cycle. So that first we would try plus, or rather first we would try parentheses, then we would try times, then we would try our new thing, then we would try plus and minus. That would require another grammatical block within our definition rather than just another loop within the one that we did. We also switched it to double, and switching it to double was pretty straightforward, but what we had to add to that was our understanding of the tokenizer had to also incorporate a floating point rather than just being a sequence of digits. And that's, of course, part of the difference between integer and double. As Tim, as you pointed out, our parser didn't handle a minus sign in front of numbers. We obviously could do that. Just leave you with a final thought. If you think about programming code, if you think about a Java file, the compiler is just a very elaborate version of that expression tree that we created. When the compiler looks at your Java code, it runs a parser that works in many ways like what we just created. But instead of looking at operators of just plus and minus, it looks for all the reserved words. It looks for for loops, it looks for integer, it looks for new, it looks for class. It goes through and it parses it, and it creates something called an abstract syntax tree. The abstract syntax tree is to Java what those little diagrams of terms, expressions, and factors is to our arithmetic expressions. So in many ways, parsing code is just an extension of what we do when we parse arithmetic expressions. And hopefully in a further future course in computer science, you'll have a chance to build a compiler that builds on this idea. We have that. It depends exactly who teaches it and which class you're taking with them. So
Would that be like a class on the project, or would that be like a small thing?
it would be probably like a third or a half of the class. Depends on how much of the class is going to be devoted to that. Because the process, when you parse those expressions, when we built up the result of those parsing expressions by saying value plus value, when you do it in code, you have to do a little bit more sophisticated work in order to make the value come back. Because what you get back is code. You parse code, you get code back. All right, any last questions online or otherwise? Okay, thank you for your attention. We will see you tomorrow. Got homework due Friday and Monday. Hope our remote people who are sick get better. Hope that our remote people who haven't been able to take the exam yet are able to take the exam. And for the people that are just following along, hello. We will see you tomorrow. Ciao.